Hi everyone. This example problem is about the chi-squared goodness of fit test, and I'm going to walk you guys through how you know that it's a goodness of fit test and then how we actually carry it out. So the first question we're always asking ourselves is, do we have quantitative data? Do we have categorical data? The data in this example, well, we've got the counts of red-eyed flies and the counts of white-eyed flies that constitutes our data. So because we have the number of observations in each of those categories, that tells us that this is categorical data. And all the tests that we have learned for categorical data are based on the chi-squared distribution. The only difference is how many degrees of freedom we used for the various situations. Now this situation is one where we just have one variable. It's the color of the eyes. The eyes can be either red or white. There aren't other variables involved. There aren't, and there's only two categories in this one variable. So when there's only one variable involved, that is a classic chi-squared goodness of fit test. And we have to figure out what the observed and expected frequencies are. That's something that we have to do whenever we're doing a chi-squared test. So we'll start off by doing that. The first thing to notice is that we do already have some observed values. There's only two categories, and we have observed frequencies for both of those categories. We know that there are 160 in the category of red-eyed flies, and there are 40 in the category of white-eyed flies, for a total of 200 altogether. So we already know that these are my O sub i's, my observed values for red-eyed and white-eyed. We also need to figure out what the kind of theoretical expected values would be for each of these categories. And that's where this information from the question comes in. If that proportion is true, then we would expect about 25% of the population to have white eyes, and we'd expect about 75% to have red eyes. And that's basically what our null hypothesis is. It's just saying, the null hypothesis is just saying that the probability of an individual fruit fly having white eyes is 0.25, and the probability of an individual fruit fly having red eyes is 0.75. That's our null hypothesis. The alternative hypothesis is just that that is not true. So while the null hypothesis is about probabilities, these numbers are between 0 and 1, they are probabilities, that's what the null hypothesis is about, but the actual procedure is going to require us to come up with these expected values in the different categories. So if I say my population is 25% white, it's 75% red eyes, then I would expect in a sample of 200, I would be able to say what I expect the number of red-eyed flies is and what the number of white-eyed flies is. So since 25% of them have white eyes, I would expect that the number in this white-eyed category out of a total of 200 would be 50. That's 25% of 200. Similarly, I would expect 75% of 200, or 150, to be in this red-eyed category. So now I have my observed and my expected values for all of the categories. I say all, there's just two. And now we have to use our formula for the chi-squared test statistic, which just uses these observed and expected values, and we'll compare that against the chi-squared table. So the formula looks like this. It's the sum of the observed values minus the expected values squared divided by the expected values. And here I'm going from I equals 1 to k, where k is the number of categories. I just have the two categories, so I'm just adding up two things here. So the first thing I'm doing is looking at the red-eyed flies. So I have 160 for my observed minus 150 for my expected. I square that. I divide it by 150, the expected number of red-eyed flies in this sample of 200. Similarly, I've got my observed white-eyed flies, that's 40. I subtract off the expected, that's 50. I square it, I divide by the expected number of white-eyed flies. And now I do the math on, or do the arithmetic on this test statistic. I've got 10 squared over 150 plus 10 squared over 50, which is 100 over 150 plus 100 over 50. This adds up to 0.67 plus 2, which is 2.67. So there is the value of my chi-squared test statistic, and I guess I'll go ahead and just write that here. This is the chi-squared test statistic, and it came out to being 2.67. So we're going to take that 2.67 to the chi-squared table, but before we go to the chi-squared table, we have to know how many degrees of freedom we have. For the chi-squared goodness of fit test, the degrees of freedom is the number of categories minus 1. So I'll just put that in its own little box here. The number of categories minus 1. So here, for this problem, we have the degrees of freedom is just 1, since there's 2 categories. So next step is we take this 2.67 and the fact that we're looking at degrees of freedom 1 to the chi-squared table. So here's the chi-squared table, and we're talking about 1 degree of freedom, and our test statistic was, I'll write it down here again, our test statistic was 2.67. So we're going to look on this 1 degree of freedom line for 2.67, and we can see it's going to have to be in between these two numbers somewhere. So that means that the corresponding probability is going to be somewhere between 0.1 and 0.2. For chi-squared goodness of fit tests, we are generally doing non-directional alternatives, and that's what this table gives. So we can say that this is the p-value that we see at the heading of the table. It's between 0.1 and 0.2. That means that if we're using a significance level of alpha equals 0.05, then we can say for sure that our p-value is greater than alpha, which means that we do not reject the null hypothesis. We do not have evidence, based on the sample data that we have here, that the true proportions differ from that which we would expect scientifically according to the genetic theory.